Welcome from Netsch Instruments to our new Research Spotlight series. I'm your host, Erica Delaney. The Research Spotlight series are virtual presentations from Netsch users on a wide range of applications demonstrating how thermal analysis contributes to their research. Today is our metals and ceramics session. Next week, we will offer a presentation on nuclear materials. Last week's session on polymers was recorded and is now available for viewing if you missed it. Information on how to register can be found on our website or by emailing us directly. Questions can be sent on the questions bar located on the tool section of GoToMeeting. Today's session is on rare earth orthoniobate materials for solid oxide fuel cell applications, shape memory, and toughening. Our speaker is Dr. Dan Lowry, who recently graduated from Oklahoma State University in the group of Professor Pankaj Saran with his PhD. He performed his research at Oklahoma State's Helmrich Research Center. This state-of-the-art facility provides research, testing, technology transfer, and education in topics around their core research focus of materials. Although Dan has completed his thesis work and is now working for Nucera Solutions, he has been kind enough to share his research with us today. So without further ado, I will turn it over to Dan and allow him to start sharing his screen.
All right. So thank you everybody for attending today. Hopefully you're able to see my screen. I don't know, Erica, if you can confirm that that's the case.
We can see your screen and we can hear you.
All right, fantastic. So again, thank you everybody for making time out of your day to attend my presentation. As Erica said, today I'll be speaking on my graduate research, which was investigating the effects of aliovalent doping on the phase transformation and thermal expansion properties of rare earth orthoniobate materials, and the targeted application was for solid oxide fuel cells. So to begin, whoops. What are the rare earth orthoniobate materials? So they are a 1-to-1 ratio of the rare earth oxide and niobium oxide, as you can see on the right side of the slide here with the phase diagram. So if you go too far off from that 1-to-1 ratio, you do begin to create the 3-to-1 or the 1-to-3. If you had to err on the side of too much, it's better to err on the side of too much of the rare earth, because if you err on too much niobium, you do end up with a electronically conductive phase, which would be bad for the proton conducting solid oxide fuel cell applications. Now, the rare earth niobates are unique in that the niobium assumes a 4-fold coordination with 4 oxygens, as you can see here on the middle figure. If we look on the left side figure, this is the orthorhombic niobium pentoxide, in which there is an 8-fold niobium and a 6-fold niobium. The 4-fold coordination is unique to the rare earth niobate structure. So these materials undergo a second-order ferroelastic phase transformation from the high-temperature tetragonal phase to the low-temperature monoclinic. Now, in the monoclinic phase, there are 2 unique oxygen positions, denoted by the green and cream spheres here, and the beta angle deviates from 90 degrees to about 94 degrees in these materials. On transformation, the oxygens are all equivalent, as you can see by all of them being green in the top figure here. Now, the phase transformation temperature is dependent upon the size of the rare earth cation. Lanthanum, being the largest of the rare earths, has the lowest transformation temperature around 500 to 530 degrees Celsius, and that increases as you decrease the size of the rare earth until you get to about dysprosium, yttrium, somewhere in here, at which point it levels out at roughly 830 degrees Celsius. Now, in our representation, the tetragonal phase, indicated by the orange solid figure here, the A and B axes are equivalent and the C axis is non-equivalent, but on transformation, the A tetragonal becomes a C monoclinic, the B tetragonal becomes A monoclinic, and then the C tetragonal becomes the B monoclinic, and the beta angle again deviates from 90 degrees. What we can see from a high temperature diffraction in the refinement of the lattice parameters is that on cooling, the C tetragonal becomes a B monoclinic, and then the A tetragonal, which would also be the B tetragonal, then becomes the A and C monoclinic lattice parameters here. Now, as it is a second order phase transformation, there's no discontinuity in the unit cell volume through transformation. Sorry about that. This is unlike, say, zirconia, where there is a approximately 3% volume increase when you go from tetragonal to monoclinic. Now, again, the potential applications for the rare earth niobate materials were shape memory applications. And if we look at the, I guess, a typical stress strain hysteresis on the right side here, you can go from a state 1, apply stress, get to the state 1 stability or stable phase. And then if you remove the stress, the strain is maintained, so it stays in that strained state until you apply a sufficient stress in the opposite direction, which can get you to state 2. And you can go back and forth between these states by applying different stresses. Also, ferroelastic toughening was an intriguing application for these materials, in that you would have the stable tetragonal phase above the transformation temperature. You could apply a stress to it, transform to the monoclinic, and then once the stress was removed, you would retain or revert back to the high temperature tetragonal phase. Now, the interesting application was as a electrolyte material for a proton conducting solid oxide fuel cell, represented by this middle region here. And this is exaggerated relative to the anode and cathode sides of a device. But on the anode side, and proton conducting is where you would have your fuel cell, where if you're doing an oxygen conducting system, it would be on the cathode side. So again, we have our fuel on the anode, from which we would remove the hydrogens, and then the hydrogen would transverse through the electrolyte layer, recombine with oxygen supplied from air on the cathode side, generating quite a bit of energy on that side. And this configuration is preferred because you're not generating any moisture on the fuel side or the anode. It is all on the cathode side. And it's also more resistant to coking, which is the buildup of carbon on the anode surface, which will reduce your efficiency. Now, as this is a ferroelastic material, it retains a good amount of strain when you transform from the high temperature tetragonal to the monoclinic on cooling. So on this figure here, we see this square, which would be representative of the high temperature phase. When it cools, it forms one of two possible states, state 1 and state 2. Now these states are equivalent, they're just different from each other in how they're oriented. And this manifests itself in a twin microstructure, as we can see here on the right side. So on this grain, we can see the different states from this banding on the grain surface. Now, 7% strain is huge. If you want to think about it in terms of something you can hold in your hands, if you were to take an aluminum can and strain it 7%, there is no chance ever of recovering the original shape of that material. Yet these rare earth niobates can withstand that high degree of strain without failure. Okay, so for my work, I utilized two major experimental methods or pieces of equipment, and the first of which was a STA 449 Jupiter simultaneous thermal analyzer from NETCH. Our system was equipped with a silicon carbide furnace and a platinum furnace. I utilized the platinum furnace primarily with a DSC sample carrier and using the platinum sample pans. So I was using the STA mostly for the specific heat measurements. Since the material is undergoes a second order phase transformation, the specific heat can be used to determine the transformation temperature as a discontinuity, which shows up as a step change. And I have multiple examples of that throughout this presentation. And for these measurements, we utilized a sapphire reference. So the other experimental method that I used was in situ high temperature diffraction, and this utilized a quadrupole lamp furnace, which is a brass body with 4 halogen bulbs on it with a parabolic gold-coated reflector, and it's the second focal plane of these lamps that's coincident within the middle of the furnace, which we can kind of see here on the right side, which generates our hot zone. So this allowed me to do the in situ diffraction using either powder samples loaded in quartz or sapphire capillaries, or sintered samples that were mounted in an alumina tube and then freely supported within the hot zone. These experiments did use mostly synchrotron sources, mostly at Brookhaven National Lab at NSLS 2. and this enabled us to use transmission geometry to minimize the effect of texturing within our samples. So from these experiments, we can see these waterfall plots of the in situ experiment. And this goes from about 20 degrees Celsius to roughly 1200 degrees Celsius. And we can see the convergence of the monoclinic peaks into the tetragonal upon heating. So as I said, a lot of this work was done at NSLS2, and this is the experiment hutch for the XPD beamline. We have x-rays coming from the right side. We did not utilize the robot. The furnace would be positioned somewhere in here. And then depending on the experiment, we could use the PDF detector for pair distribution functions and total scattering. But everything I'm presenting here would have utilized the detector on the far side for the diffraction experiment. Now, as I said, we can use a specific heat measurement to determine or identify the transformation temperature. But for a more accurate complementary method, we can do a spontaneous strain calculation from the in situ diffraction experiment with the refined lattice parameters. And this allows us to apply Landau theory to determine the phase transformation temperature. This is especially important when there were the coexistence of both the low temperature and the high temperature phase due to some of the doping strategies. To determine the transformation temperature from the Landau experiment, or from Landau theory, we would have spontaneous strain, which was calculated from the results here, which is equal to K times the quantity 1 minus T over T TR to the eta. K is just a proportionality constant. If we set eta equal to 1/2, that's for a second order phase transformation. And then we can determine the transformation temperature from a least squares fitting. Now, also from the diffraction experiment, we can determine the thermal expansion tensor. As a second rank tensor, there are 6 unique elements, which from that you can determine the eigenvalues of expansion, which represent the maximum or minimum directions or magnitudes of expansion. And if you have the eigenvectors, you can determine, or the eigenangles, you can determine the directions as well. So for the monoclinic, there are 4 unique tensor elements, the 1, 1, 2, 2, 3, 3, and the 1, 3. For the tetragonal, we just have the 1, 1, 2, 2, and 3, 3, which then become the eigenvalues. Eigen 1 is equal to eigen 2, not eigen 3 for tetragonal, and the eigenvalues are all unique for the monoclinic phase. Okay, so for my work, the experimental method followed kind of the flow charts here. For synthesis, we'd take the rare nitrates, mix those with the niobium chloride, and then whichever dopant, magnesium, calcium, strontium, barium, or zirconium, dissolve that into ethanol, to which PEG would be added as a entrapment material. And what the PEG's doing is serving as a molecular net to hold all of the metal cations in a homogeneous mixture. This was then dried out under mixing and then calcined, and then depending on the intended experiment, they were calcined from between 600 Celsius to 1200 for a range of times to generate the oxide material. And then this was then ground and sieved through a 325 mesh. So for the experimental approach, for the DSC and CP, or specific heat studies, the powders were pressed into a 6mm disc, which was then centered and then measured under 3 thermal cycles from roughly room temperature to 1500 degrees Celsius. For specific heat, I utilized a 20 degree a minute heating rates. And then for the high temperature diffraction, for the powder studies, the ceramic powder was mixed with platinum. And this platinum just served as an internal temperature reference. You can, from the refinement of the platinum lattice constant, you can accurately determine the temperature of your sample. This would then be loaded into a quartz capillary. Quartz was preferred over sapphire because my transformations were expected to occur less than 1200 degrees Celsius, and I did not have to account for the sapphire peaks that would result from using those capillaries in the diffraction data. And again, we were limited to about 1200 degrees Celsius because then quartz devitrifies and the sample just breaks. Also, I could use, for the freestanding centered samples, these would be pressed into a disc, centered at 1500 Celsius for 10 hours, cut into roughly 1mm by 1mm cross-section bars. To this, a surface would be coated with platinum ink, and then the powder, again for that temperature reference. And then after the data was collected using the Rietveld refinement method, that would determine the phase transformation from the Landau theory as well as the thermal expansion. Okay, I'm gonna take a quick drink, sorry. All right, so the first approach to doping these materials was aliovalent doping of the rare earth site with a 2+ cation, and this was the magnesium, calcium, strontium, or barium. The purpose of this was to generate oxygen vacancies within the lattice, and this is necessary to increase the proton conductivity of these materials for the SOFC applications. Now, beyond this, my interest was what is the effect on the phase transformation due to this doping, as well as on thermal expansion. So first, in lanthanum niobate, I looked at the effect of all 4 of the 2+ elements, magnesium through barium, in 1 mole% doping concentrations, as well as 2 mole%. So on the right side here, we see the specific heat data. And from this, we don't really see much of a change in the transformation temperature due to doping. So from the CP, we took the endpoint on heating as the transformation temperature. So from CP, we don't see much difference. And then looking at the refined lattice parameters, there's not a whole lot of difference due to the doping as well. One indicator that we would have used is a significant change in the room temperature spontaneous strain to identify either a potential increase or decrease of the phase transformation temperature. And as you can see here, the spontaneous strain did not change much due to this doping. Now, however, when we look at the actual numbers from specific heat, we see that there's not a whole lot of difference in the transformation temperature of this material, from roughly 500 Celsius for the pure material to maybe an extreme of 526 with 1% barium. But that 526 Celsius is well within the expected range of the phase transformation for the pure material. As I said, it's been reported anywhere from about 500 Celsius to 530 degrees Celsius. Now, if we look at the spontaneous strain, we see that there's a significant increase in the transformation temperature due to this doping. And then using what I'm calling here the beta prime angle, which would be beta minus 90 degrees. Again, 90 degrees is for the tetragonal structure. So the difference between the monoclinic and the tetragonal is the beta star. And we can substitute, or beta prime, we can substitute beta prime into this equation for spontaneous strain. We see good agreement between the calculated transformation temperature using Landau theory with these 2 different parameters. Now, if we look at this figure here that I'm kind of hovering over, this is the spontaneous strain of the material with regard to temperature, and we see that this fitted dashed line, which comes from this equation here, increases as we increase the size of the dopant cation. Strontium's a little strange in that it exceeds, or it goes well beyond that of barium, but we see with regularity that it's consistently going, the transformation temperature is going up due to cation doping. Now, beyond that, looking at the effect of doping on the thermal expansion, we see that on these left figures here, the solid squares is the pure lanthanum niobate, and then the hollow squares is the pure lanthanum niobate for tetragonal. So tetragonal here, monoclinic here. We see that the doping decreases the magnitude of thermal expansion in the lanthanum niobate. Beta is the sum of the eigenvalues. If we were to take the average of the eigenvalues, that would be the average linear expansion, which you could then compare with a dilatometric measurement for thermal expansion. So we see that with this doping, we've decreased the thermal expansion of the monoclinic phase, but the tetragonal phase kind of increases in the overall magnitude. These right side figures here show the aspericism of the thermal expansion, and this is a property that would be difficult to measure through other in-lab methods, but the high temperature diffraction and thermal expansion analysis allows us to do this. Now, aspericism represents the anisotropy in the thermal expansion. As a monoclinic is a very anisotropic structure, only way you can get more so is by going to triclinic. We expect a high degree of anisotropy in the thermal expansion of the monoclinic phase. But what we see here with 1% doping is that it is less anisotropic due to the doping. And then through the phase transformation, we would expect a discontinuity just as you change that crystal structure and symmetry. So moving beyond the alkaline earth doping of the lanthanum niobate, we looked at the doping of dysprosium niobate with magnesium. So in this case, we looked at doping concentrations of 1 mole% to 5 mole%, and only looking at magnesium. And this was to match the size of the dopant cation as much as we could to the rare earth, to the dysprosium, utilizing the ionic radius as our comparison factor. So for this experiment, again, we're doing the high temperature diffraction. This is where I utilized that sintered rod, freely supported. And we were able to go from 20 degrees Celsius to just shy of 1700 degrees Celsius, and then still acquire that data on cooling because we didn't have to worry about the sample itself breaking. So that's what we can see here, the heating, and then again, the cooling and the reversibility of the phase transformation. What was there at the beginning is what was there at the end after cooling. Now from this, again, looking at the specific heat data, we don't expect any change in the phase transformation due to doping, as this endpoint hasn't changed. And then if we look at the refined lattice parameters and the calculated spontaneous strain, again, there's really no difference due to doping. Now, unlike with the doping of lanthanum niobate and dysprosium niobate, it was determined that magnesium, in fact, does not change the phase transformation temperature. The calculated temperatures within the error were all the same. But if we look at that volume expansion, again, there's not a whole lot of change in the low temperature phase, but what we saw was an increase in expansion of the tetragonal phase due to the doping concentration. So again, like I said, using the high temperature diffraction to determine thermal expansion, we can calculate the entire thermal expansion tensor, and from this we can determine the thermal expansion in any direction. What this slide here is showing is a two-dimensional representation of the thermal expansion ellipsoid at discrete temperatures. So each of these goes from about 275, or is from 275 Celsius to 825 Celsius in 25 degree steps. Now we see that for pure dysprosium niobate in the dope 2% and 4%, there's not a whole lot of change, and that was shown in the previous slide. Not a lot of change due to doping, but we do see the large degree of anisotropy in the thermal expansion of the monoclinic phase. So this top one is going to be looking at the 001 plane or down the C-axis, where the bottom ones are all going to be looking down the B-axis or at the 010 planes. Now, what was interesting for this, for the 2+ doping of the rare earth niobates, and I wasn't able to really pursue this much beyond what I'm going to show you right now, is that at temperatures beyond the phase transformation, so here on the left, we're looking at the magnesium doped dysprosium niobate. This region right here would be the what we saw in the CP measurement as well. But if we go beyond that, we see this additional transformation. Again, I'm not sure what this represents, was not able to investigate this further, and it did not show itself in the high temperature diffraction experiment. But that as we increase the concentration of magnesium, the secondary reaction is becoming more and more prevalent. This also happened in the calcium doped lanthanum niobate. It would have happened in the other ones as well. This was the only data I had to cover that temperature range, but it's a reproducible. So from the solid to dashed is going to be the first to the second heating cycles. But the second transformation was of interest and something that still sticks in the back of my mind that I would like to investigate further. Now, the other major aspect of this presentation and of my research was the effect of zirconium co-substitution of the rare earth niobates. So in the previous section, the dopant only sat on the rare earth, and we're replacing a 3+ with a 2+. In this case, zirconium sits equally on the rare earth and the niobium sites. So we're replacing a 3+ and a 5+ equally with a 4+. So we maintain the overall charge of the material, keeping the O4 and preventing the formation of a defect in the form of oxygen vacancies. And again, our interest was on the effect of the phase transformation and the thermal expansion properties. So the motivation for this part was a study of yttrium tantalate here on the right side with zirconium co-substitution. The rare earth tantalates are important to note that it is important to note that they have the same structure as the rare earth niobates, they undergo a similar or the same transformation mechanism, just at a much higher temperature. In this case, yttrium tantalate transforms around 1,460 degrees Celsius in the pure form. You can compare that to dysprosium niobate and yttrium niobate, which transform around 830 degrees Celsius. Now, in the yttrium tantalate from this group's work out of Harvard, with 20 mole % zirconium co-substitution, they were able to decrease the transformation temperature from 1460 down to around 850 degrees Celsius, while also stabilizing the high temperature phase at room temperature. Now, this is important to note because as a second order phase transformation, it is not possible to stabilize the high temperature phase through a quenching mechanism. It's an instantaneous transformation. There is no time dependency, and you cannot stabilize it through quenching. Again, on the left side here, this is just the figure from earlier, showing that the phase transformation temperature of the niobates increases as the radius of the cation, of the rare earth cation, decreases. So in this first section, I'm going to show the effect of zirconium co-substitution on lanthanum niobate and yttrium niobate. For the dysprosium niobate, that'll come after. I went to higher substitution concentrations. So what's interesting to note here is that the refined lattice parameters do not show much of a difference due to the incorporation of zirconium. In lanthanum niobate, there's a limit of roughly 4%, which is why we capped it at around 4% here. But what's interesting is that the crystallite size, or the average crystallite size of the monoclinic phase, decreases due to the increasing zirconium concentration. Now, if any of you are familiar with stabilization or yttria stabilized zirconia, we know that there is a relationship between the crystallite size of the zirconia particle to stabilization of the tetragonal phase. With the yttria doping, you can increase that critical size, but even in pure zirconia, you can stabilize the high temperature phase below transformation if your particle size is sufficiently small, and that's represented by the crystallite in this data here. So further, if we look at the yttrium tantalate, again, or yttrium niobate, my apologies, there's not a lot of change in the lattice parameters due to zirconium co-substitution, but the crystallite size is decreased to about 20% of the pure with just 4.36% zirconia. And we see that we stabilize a little bit over 8% of the tetragonal phase by volume at room temperature. And also for the tetragonal phase, with the higher zirconia co-substitution, it has a larger crystallite size, indicating a role of the crystallite size in the stabilization of both of the high temperature phase below transformation. Sorry, it's a bit dry here. So again, moving forward, the first major measurement done on these materials was a specific heat measurement. So for the lanthanum niobate, we see that there's not a whole lot of change to the endpoint of the specific heat feature here due to the zirconium co-substitution. And if we were to think back on that previous slide where there wasn't a lot of change, or the crystallite size of this material is still very large, we don't expect a whole lot of change in the phase transformation due to zirconium co-substitution for the lanthanum. Now looking at dysprosium and yttrium, we see a nice decrease in the specific heat change due to the incorporation of the zirconium. All right, so looking here at lanthanum niobate, dysprosium niobate, and yttrium niobate with the similar concentrations, as expected, not a lot of change in the lanthanum niobate phase transformation due to zirconium. But what we see here for the dysprosium is a decrease of roughly 60 degrees, and for the yttrium niobate, roughly 90 degrees change due to fairly small loadings of zirconium co-substitution. And then from here on this middle figure, this is at spontaneous strain with respect to temperature. And we see that the curves are all relatively the same. For the lanthanum niobate, it comes in much lower. That transformation, again, as we can see, is roughly 300 degrees lower than that for the dysprosium and yttrium niobates. And then on this right side figure, again, on the y-axis is the spontaneous strain, and then the x-axis is just normalized to that calculated phase transformation temperature, still showing that the mechanism of the transformation has not really been modified due to zirconium co-substitution, it is still a second order phase transformation. And again, looking at the thermal expansion analysis from that high temperature diffraction, we see here for the lanthanum niobate that the volume expansion has decreased due to the incorporation of zirconium in the monoclinic phase, but that in the tetragonal with the higher loadings, we have increased the magnitude of expansion. For the yttrium niobate, there was not a lot of change either way for the monoclinic or tetragonal phase due to that up to about 4.4% of zirconium. And in the aspericism, which again is the anisotropy of thermal expansion, we see an increase in the anisotropy for the monoclinic phase, but a decrease in tetragonal for the lanthanum niobate, and again, not much change for the yttrium niobate. Okay, so moving on, for the zirconium niobate, I looked at much higher loadings or concentrations of the zirconium co-substitution, going from 0, so pure dysprosium niobate, up to about 19 mole% of zirconium incorporation. So the data here on the left is just room temperature diffraction, and then zooming in on that red square here on the right, you see the monoclinic peaks here on the outside, what kind of appears as a shoulder, but then the tetragonal peak, which is indicated by the diamond in the middle. If you think back to those waterfall plots, the convergence of the monoclinic to the tetragonal, that's what we're seeing here, but at room temperature due to the increased stabilization of the tetragonal phase. Now the square here represents what is the O2O plane in the monoclinic and the O02 plane in the tetragonal, and those are invariant. So one just transitions into the other, and that's due to the we can call that due to the orientate or the unit cells that we chose to describe these these phases. So here, looking at the effect of zirconium co-substitution on the lattice parameters, we do see that the A and the C become closer to each other as we increase the zirconium concentration, which is expected, and that the long axis shortens. If we look at the crystallite size, we see that with increasing zirconia, that's decreasing significantly. And then, as I mentioned previously, it's possible to stabilize the high temperature phase if you have a small enough crystallite size. So in this case, we are able to decrease the crystallite size of the tetragonal phase sufficiently in the pure system to stabilize just over 3% by volume of, by volume of the tetragonal phase. But then as we increase the amount of zirconia, we've stabilized about a third of the material as tetragonal. And here we see that the zirconium is actually decreasing the crystallite size of the tetragonal phase as well. So on the right side here, we see that the transition temperature has decreased due to the zirconium co-substitution, and that the amount of tetragonal phase increases. So to further look at that, again, the specific heat measurements of the zirconium co-substituted dysprosium niobate, the solid black one here would be the pure dysprosium niobate. And then as we increase the zirconium concentration, this shifted down to lower temperatures. But then at sufficient concentrations, as you can see here on the extreme of the 19%, we really can't see the change in the CP due to that increase in the tetragonal phase at room temperature. Again, this is where the high temperature diffraction is a nice complementary method to the specific heat measurements, because we can determine the phase transformation regardless of how much tetragonal phase is in the material, since we can refine the lattice parameters of the tetragonal and the monoclinic without any influence upon each other. So from that, using the calculated spontaneous strain, we determined the phase transformation temperature using the Landau fitting. And as I said previously, we were able to decrease the transformation temperature by about 60-70 degrees Celsius. Not as significant as in the yttrium tantalate, but again, we're starting at a lower transformation temperature to begin with. And then looking at the right side here, normalizing the spontaneous strain to the room temperature value and the temperature by the determined transformation temperature here, we see that all of the data overlays itself, and we have not changed the mechanism of the phase transformation due to the zirconium co-substitution. So to summarize some of those previous results, on the right side here, this would be the determined transformation temperature from the high temperature diffraction for the lanthanum niobate, yttrium niobate, and dysprosium niobate. And on the left here, I've shown how we decrease the transformation temperature due to zirconium co-substitution for those same systems. And that's overlaid on the previous figure that I showed. So from the thermal expansion analysis, kind of disregarding the 16% zirconium sample where it did something a little weird, still haven't figured that one out. We see that the increase in zirconium concentration has decreased the thermal expansion, the volume thermal expansion of the monoclinic phase, and the tetragonal really hasn't changed. But what's interesting is that we're able to minimize this discontinuity, or the magnitude of discontinuity between the two phases for thermal expansion. And this would be very important for that oxide fuel cell application, where it's desirable to be at the high temperature phase temperature range, or within the temperature range, or beyond the thermal, or beyond the transformation temperature to get to the high temperature phase for operation due to increased symmetry and conductivity values. And then for the anisotropy, or the asphericism, unfortunately, we did see an increase in the degree of anisotropy of the thermal expansion for these materials due to zirconium's co-substitution. So just to summarize some of these results, for aliovalent doping of the rare earth niobates, did not alter the nature of the phase transformation, which was important. It is still second order and reversible, ferroelastic. But the doping of lanthanum niobate resulted in increased transformation temperature while also reducing the thermal expansion anisotropy, and magnesium doping into dysprosium niobate did not modify the transformation properties with up to 5 mol% concentration. And then for the zirconium co-substitution in the rare earth niobates, for lanthanum niobate, really no effect on the phase transformation. Lanthanum is already very large, zirconium is considerably smaller, so we weren't able to change the unit cell properties enough there. But we did reduce the thermal expansion of the niobate phase. And as we did see, there was a decrease in the crystallite size, so through some additional processing considerations, it should be possible to stabilize some of the high temperature phase at room temperature. Now for yttrium niobate, we're able to reduce the phase transformation temperature with a minimal effect on the thermal expansion, but we did see stabilization of the high temperature phase down to room temperature. And then for dysprosium niobate, similar results, a reduction in the phase transformation temperature, stabilization of 33% tetragonal, as well as a discontinuity, a decrease in the discontinuity in the volume expansion between the high temperature and low temperature phases due to increasing zirconium concentrations. Again, I'd like to acknowledge my advisor, Dr. Pankaj Sareen here at Oklahoma State University. Also grateful to him. He did bring me out to Oklahoma for my graduate studies. I worked with him previously at University of Illinois. My research group members here at Oklahoma State University, many of whom are attending this presentation today. The Beamline staff at NSLS2, Dr. Dorhe, Dr. Ghosh, and Mr. John Trunk, as well as Dr. Feng Liu there at Oklahoma State University Hellmark Research Center, with his assistance with my experiments that I completed within those facilities. And then there at the bottom, some of the acknowledgements for the national labs supported by the DOE, as well as the Oklahoma State University facilities. This time, I'd like to say thank you again for attending this presentation, and I would be happy to address any questions that you may have.
Thank you very much, Dan. Everyone, again, questions can be sent using the questions bar located on the tool section of GoToMeeting. I will take control back of the screen. So should be showing my PowerPoint again. So thank you for attending. Just while you get your questions in, I wanted to remind everyone that on October 28th, we'll have another presentation on the thermal analysis of advanced nuclear materials. Oh, so someone said my screen is not showing. So
There we go.
there we go. So on October 28th, as you can see, we'll have another presentation on thermal analysis of advanced nuclear materials, and the recording for the thermal analysis and dynamic mechanical analysis of dual curing resins in 3D printing, which we had last week, is already available, and this talk will be available as a recording if you want to watch again, or if you happen to miss something or want to scroll through. So I am not seeing any questions in the question window yet, but I will ask one. So you had the secondary reactions of the lanthanum doped niobates, and you said you wanted to look further at that because you didn't really understand them and didn't really know what was going on there. So what's your theory, and what experiments would you have done if you had endless time?
So our thought on it is, since it only occurred in the ones where we generated these oxygen vacancies with the 2+ doping of the niobates, that it has something to do with the ordering or disordering of those vacancies. If I had to choose an experiment to investigate that further, it would be high temperature neutron scattering, where we can get a more direct visualization of what the oxygen positions are doing. With the X-rays, there's not as much interaction with oxygen, so we couldn't see that structurally. So that's kind of the direction we wanted to go. Again, unfortunately, with the choice of the rare earth materials, neutrons are hard to access. But the lanthanum niobate, it would be possible to study those with the high temperature neutron scattering.
Cool, very cool. And I'm still not seeing any other questions. So with that, I will thank you very much for sharing your work with us. And if any questions do come up afterward, please feel free to email us, and we'll get them sent over to Dan so you can get some answers.
All right.
Have a wonderful day, everyone. Bye now.
Thank you again.